Okay, so today we can actually start our proof of the inverse function theorem. Remember last time we reduced the inverse function theorem to a special case. So since that work is already done, now we can just prove that special case. So here's a statement of our special case. Let E be an open subset of Rn, and let F be a C1 function from E to Rn, noting that it's the same n here and there. And let A be some point in E, then if f prime A is the identity, so this is why it's a special case. In the full inverse function theorem, you just assume here f prime A is an invertible linear map, but here we're assuming it's the identity linear map. Then there exists some open neighborhood some open set U such that let me write it like this: U is a subset of the domain of F, such that it's a neighborhood of A, and the way we've been writing it is there's these three conditions, 1, 2, 3, that hold. So there are these three components to the inverse function theorem, and I slightly regret ordering them in this order because the most important one is now number 2. Probably should have been number 1, but I'm sticking to the order that I chose because of consistency. Okay, so F restricted to U is injective. That's the most important. In other words, F is if the derivative of F is the identity at A, then F is an invertible function in some neighborhood of A. You could say, F is an invertible function in some neighborhood of A. If you were to apply this result to a situation where you know that F prime is invertible for all points A in E, then you could draw this conclusion that the inverse function theorem provides for all points A in the domain. Then you would say F is locally invertible. Locally invertible, meaning at every point there's some neighborhood U of that point where F is invertible on that neighborhood. Okay, and number 1, the image of U, which we might call V, is open. And number 3, if you take the inverse, so this will be a bijection from U to V, and if you take the inverse of this, then this is a C1 map. So then not only is it saying F is invertible near to A, but is differentiably invertible. The inverse is differentiable and even continuous, with continuous derivative. Okay, so again, this is a special case, and the reason is I'm not assuming F prime A is invertible, I'm assuming much more, that it's actually the identity. Alright, so we're actually going to start by proving number 2, then number 1, and then number 3. And we might not get to all of them today, I'll just see how long it runs and find a good stopping point. So let's start with number 2. So F prime, well, before we start with any of them actually, we need to come up with what U should be. And here's how that's going to work. So we know F prime, which is going to be a map from E to linear maps Rn to Rn, or if you like, linear operators on Rn. We know that this map is continuous, right? That's what it means to say F is C1. And specifically, we care about continuous at A. So it's continuous at A, and we know the value that it takes at A is the identity map. So that means that if you let the inputs here vary away from A by a small enough amount, then the output should be not so far away from the identity linear map. So we're gonna make U be a set on which, if you vary the input, so it'll be a neighborhood of A, such that if you let the input to f prime vary in that neighborhood of A, the output is no more than 1/2 away from the identity linear map. So let's see. Then there is some delta greater than 0, so this is me using the continuity of this function, f prime, from the metric space E to the metric space L Rn Rn. There's some delta greater than 0 so that whenever x is within delta of A, so in the delta ball of radius delta centered at A, we have f of x is within a certain distance of f of A, which is the identity. And here I can put any positive number I want. Any positive number I want. And I choose 1/2. Then we're going to let U be this delta ball centered at A. So that will be our U to prove that there is some open U such that blah, 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 blah. This is our U. And we're going to prove 1, 2, and 3 for this U. Okay, so my first goal is going to be to prove number 2 here, which is that when you restrict f to U, that's actually injective. So proving 2 now. So now I'm going to define a function, and it's going to seem kind of random at first, but just bear with me. So for each y in Rn, we're going to define a function, phi sub y, which will be from E to Rn, and it'll be defined by this formula. Phi sub y of x will be y minus fx plus x. Okay, so this is a whole family of functions, one for each n-tuple y. And you can kind of see, so, you know, if you fix y equals 0, you know, the 0 vector in Rn, then this is just like x minus f of x. So it's sort of a function that measures the displacement vector between the input to f and the output from f. So it's one of these typical things that you would apply a fixed point theorem to, like our contraction mapping theorem. So it's not too unfamiliar, I hope, of a function to see like x minus f of x. But for some reason, we're shifting it by y. So as you change y, you're looking at different ones of these x minus f of x functions, each one shifted by y. Now, why should these be useful? Well, here's the motivation. So observe that for one of these functions, phi sub y, to have x as a fixed point, this is what would have to happen. So you'd have to have y minus f of x plus x. That would have to equal x, right? So in other words, y minus f of x would have to equal 0. So in other words, y would have to equal f of x. Okay, so for the function phi sub y, for x to be a fixed point of it is for x to be one of the preimages of y. So one of the inputs that map to y as an output. Our goal in proving number 2 is to prove that f is injective. Injective means every output has only one associated input that could lead to that output. So everything that arises as an output, or every y here, should have only one preimage, x. So what we're trying to prove becomes the same as proving that if you fix y and look at the function phi sub y, then it has no more than one fixed point. Okay, so that's the purpose of this family of functions, phi sub y, is that it's a family of functions such that fixed points for them correspond to this idea of x being a preimage for y. So i.e. x is a fixed point of phi sub y if and only if x is one of the preimages of y. Alright, so it's because of this property that we will be able to apply our contraction mapping theorem in a useful way, and you'll see how. And you'll see also that these functions phi sub y are going to be useful in other ways. So these are really the star of the show in the proof of the inverse function theorem. Specifically in this proof, the one that is that I'm sort of drawing inspiration from Rudin's proof. There are other proofs not necessarily following Rudin's same approach. Okay, so remember in the previous lecture, lecture 6, we looked at, so we established a few simple results that I just didn't have a reference for at that time. One is that the derivative of any constant function is 0, and 2 is the derivative of a sum of functions, a pointwise sum, is the sum of the derivatives. So this tells us, so using those results from lecture 6, hang on, let me look it up. It was part 2. Phi sub y is differentiable, and the derivative phi sub y prime of x is going to be, so the mapping x goes to the constant y, here y is fixed, right? Fixed y. The mapping x goes to y is a constant function, so the derivative of that is 0. Then the mapping x goes to negative f of x, that's going to have for its derivative the derivative of f at x, negative, and the mapping x goes to x is going to be the identity map, which has for its derivative the identity map. The identity map is a linear map, right? And anything linear, a linear map is its own derivative. So to be a little bit more explicit just for a moment, I'm looking at this mapping. This is phi sub y, right? And so I'm viewing it as the pointwise sum of these three mappings. One of them is x goes to y. One of them is x goes to minus f of x. One of them is x goes to x. You know, I guess I didn't, in lecture 6 part 2, I didn't mention how the minus sign gets handled, but maybe I'll just leave that as something you can probably work out yourself, that the minus sign can pull out of the derivative. Yeah, so the derivative of this mapping is going to be a sum of 3 parts. It's going to be a sum of 3 linear maps. The 0 linear map, which is what I get when I take the derivative of this mapping. The linear map f prime of x, negative, which is what I get when I take the derivative of this mapping and evaluate at x. And identity, which is the linear map I get when I take the derivative of the identity and evaluate at x. So that's where I'm adding these, that's where this is coming from. Okay, and this is for all x in E that this works. And it's also, I'm doing this for each one of the phi sub y's, for each y in Rn. Okay, so I'm looking at this derivative, and let me write it differently. Let me write it as identity Rn minus f prime x. So I'm looking at this derivative, and the derivative of phi sub y at x looks like it's the distance between the derivative of f at x and the identity, which is exactly what I controlled inside the set u. So back here, whenever x is within delta of a, whenever x is in u, I have that f of x is within 1/2 of the identity. So whenever x is in u, f prime of x is within 1/2 of the identity, meaning this, which is this, is less than 1/2. All right, so that's telling me that inside u, the derivative of phi sub y is bounded in norm. That puts a restriction on how much phi can change as I vary points inside u. And to get a hard limit on exactly how the bound on the norm of the derivative restricts how much the value, the outputs of phi sub y can actually change, for that I should use Theorem 9.19. Now, Theorem 9.19 should only apply to a situation where the domain is convex. And here I'm going to say, I'm going to apply Theorem 9.19 to phi sub y, but just on u. I'm only applying it to u. And here's the result. Notice that u is convex, by the way. U is convex because it's a ball, and Euclidean balls are convex. So I can apply Theorem 9.19, and I get that for any x1, x2 in u, the distance between phi y of x1 and phi y of x2 can be no more than 1/2 the distance between x1 and x2, where this 1/2 is the capital M that shows up in the statement of Theorem 9.19. So now it's tempting to say that phi must be a contraction mapping, right? This is the inequality that tells you that a map is a contraction mapping. The distance between two outputs is going to be a constant factor, bounded above by a constant factor less than 1 of the distance between the inputs. So this is exactly what a contraction mapping is, right? Except not yet. So we cannot say phi is a contraction mapping because it does not necessarily map u into itself, right? In the setup for a contraction mapping, we were talking about a function that maps a metric space like x to the same metric space. But all we know is when you focus on phi sub y restricted to u, all we know is that it maps u somehow into Rn, but we don't know exactly we don't know that it maps U into U. Also, the space X needs to be complete in the contraction mapping theorem. So we don't know that U is complete. In fact, we don't expect it to be complete. Probably if U, well, no, we know it's not complete. U is just an open ball, so it's not complete. All right, so we are not yet in a position to apply the contraction mapping theorem. But we can at least apply the uniqueness idea in that theorem. So I now claim that we have proven that F is injective. And here's the argument as to why it follows from this. If, say, f of x1 equals f of x2, and let's call that y, so let's define y for the moment to be whatever is this common output. When you plug in x1 or x2, you get y. Then look at phi sub y, where it's this y that I'm putting as a subscript of x1 minus phi sub y of x2. Look at the distance between these two. According to above, here, not f is injective, I'm sorry. F restricted to u is injective. So here I get to assume x1, x2 are in u, where x1, x2 are in u. Then when you look at this, according to the statement above, this is less than or equal to 1/2 the distance between x1 and x2. And according to this observation, which is off screen at the moment, according to this observation that if x is a preimage for y, then it is a fixed point for phi sub y. According to this observation here, since x1 and x2 are both preimages for y, they are both fixed points for phi sub y, meaning that this is just x1, and that's just x2. So look what we've got. This number is less than or equal to 1/2 times the same number. This can only happen if the number is 0. So therefore x1 equals x2. And that's injectivity, right? So if x1 and x2 are in the set U, then fx1 equals fx2 gives you x1 equals x2. And 2 is now proven. So we have not yet used the contraction mapping theorem. We just use an idea from the proof of it, which is the uniqueness aspect of it. And we've proven that f restricted to U is injective. So here's the theorem on display again, our special case of the inverse function theorem, and we've proven number 2. And remember, once the special case is done, the inverse function theorem proof is done, because last time we reduced the full theorem to this special case. So it remains to prove 1 and then 3.